Hey, this is Horner, and these are the concept questions for number 1 through 10 for circular motion and torque. For this very first one, it says, which has a greater linear speed? And they want to know, is it on a merry-go-round? Is it going to be the outside horse, or is it going to be the one that's on the one near the rail? So outside rail or on the inside. So you can see the horses here, but I think it's a little easier to see this. So if you had a horse here and then you had a horse on the very outside, the one that's going to have the bigger linear speed is going to be the one that is on the outside. This one's not going to travel as quickly as this one does. If you're not sure about that, twirl yourself in a circle, put your thumb up, and you'll actually see that your thumb is moving very, very quickly. Or grab a hold of somebody and have them try to run on the outside as you stand in the center just kind of twirling. So it is the outside horse that has more linear speed. For number 2, they want to know which has a greater angular speed. Angular speed, it doesn't matter whether I'm standing here, here, or here. We all will take the same amount of time to go all the way around in the circle. So on this one, it wouldn't matter who it is. We all take the same amount of time to go all the way around once. So that means that they both have the same angular speed. So angular speed is how many times it goes around in a particular unit of time. So if, for example, this thing might go around 10 times in a second. And if that's true, that dot, and that dot will all travel 10 times in 1 second around. The one with the higher linear speed is going to be the one on the outside. But this one says angular speed, so they are all the same. For number 3, it says, which of the following unit is a unit of rotational speed? Revolutions per hour is a rotational speed. If I want to know the revolutions per minute, the revolutions per second. So those are all units of rotational speed. So just be careful with that. They're all the same here, but on the test they won't be. And on your quizzes, you'll see that it'll say which of the following is not a unit. So just remember that these are, and anything turning per hour, minute, or second. So the number of revolutions are the number of turns per unit time. And those are good units of rotational speed. What is the direction of the force that acts on the clothes in a spin cycle in a washing machine? Well, if you remember, these clothes are spinning very fast, so we're trying to pull them towards the center. We're trying to pull all of these towards the center. And if you pull them towards the center, then that is an inward force. So the water is actually the holes in the tub allow the water to come spinning and they actually spin out of the tube because there is, or the tub, because of the holes. So they actually travel tangent, they hit the tub, and then they run down. Pretty nifty little device. Number 5 says a car travels in a circle with a constant speed. The net force of the car, and you can actually see it here, actually points towards the center. So all of these would have a force pointing towards the center. What is that force? That force is going to be the force of friction, pushing it towards the center. Next one, number 6, when a railroad train rounds a banked track, the centripetal force needed comes not from friction this time, but actually comes from the normal force. So this would be the normal force. Going straight down for the car would be its weight, or mg. So this actually comes from the normal force itself, or the horizontal component of the normal force. So on this one, it's pretty close, but this would be the horizontal component of the normal force. The vertical component would kind of keep you in your seat. Otherwise, you would totally fall out. That would be bad. That would not be good. Number 7, the centripetal force exerted on a stunt motorcyclist biker bobble riding on the inner vertical surface of the circular track. And this one, go figure, is the normal force. So here we've got the normal force actually pointing straight in. It is the same thing as the centripetal force, so we can make those exactly the same. For number 8, this one says Nellie Newton swings a rock in a circular path while holding an attached string overhead. The string makes a 45-degree angle, so here's the angle. And we call this a conical pendulum. It looks like a cone. So if we actually finish this, you would see that this whole thing would look like a cone. So we could put a front on it, and then you would have a cone type of surface. The centripetal force that holds the rock in the path is the horizontal component of the string tension. And so you can here see that Ft, so that is the horizontal component of the string if we're thinking about using the angle that is right here. So if you're using this angle theta, which is the same one as this one, you'll see that the horizontal component of the string tension is the one that holds it in that circle. For number 9, centrifugal forces. These are forces that are fake. So notice the word centrifugal is not a physics term. It is a fake force that makes you feel like you're getting pushed out. Kind of like these people are feel like they're getting pushed out on this rotor ride. Is apparently a reality to observers in a reference frame. So they are actually turning in this reference frame. So they are rotating. So to them, they feel like they're getting pushed out. To us, we see that they're getting pulled in. Kind of a neat little ride. This one, the Earth is spinning. I'm going to actually go back and do that one again. So here, this one is actually spinning. So let's see if we can get the thing to come back. There we go. A person weighs less at the equator than at the poles. Why? Well, it's because the Earth is rotating. You'll notice that it is rotating very fast tangentially here. And if you're up here, it is rotating very slowly. So when we start this animation again, you'll notice that if you're moving faster, the force of gravity is having a little bit of trouble trying to keep up with you because you are moving so quickly in this direction that you're actually getting thrown off the Earth a little bit more. You're trying to travel more tangential speed-wise to the Earth than somebody standing here. So if you looked at the side of the Earth and you were standing right here, and somebody else was standing here, we know that our tangential speed here would be very fast, so you would be getting thrown off behind going straight into the page, and they would have just a little bit of that. Because of that, and because there's a component that goes this way, we could also say that your mg is going in this direction. The mg has more of an effect here than it does here. So this has to do mainly just with the spin of the Earth. Is trying to throw you off, but gravity keeps pulling you in. Next one is number 11. This one says, as the rotational speed of a space habitat increases, the weight of the people inside should also increase. Notice that as this thing spins faster and faster, that the centripetal force will get bigger and bigger. So you feel like you're getting heavier and heavier as you spin in that. For number 12, a tin can is rolled on the end of a string, so we're going to pretend that these tennis balls are really tin cans. And as it is swinging in the circle, it swings in that circle because the tension is actually pulling that can in. So there is a force of tension that is pulling it towards the hand. And then there's also a pull from the can on the hand, but this keeps it moving in a circle. So we don't have to say centripetal force, we can just say tension or normal force. If the Earth rotated a little bit more slowly, your weight would increase. So remember your weight, so here's the Earth, if it's spinning and you're standing on it, and let's say that it's rotating in this direction, your mg would go straight down, but then there would be a component of your weight, component of the spin, so the spin goes in this direction, there'd be a component of that spin that would also go in the opposite direction, and that would, if the Earth wasn't spinning as fast, that little arrow would get less because this arrow would be less. And so you would actually be a little bit heavier. So the Earth spin does have to change that a little bit. We can also look at the equation and do it that way. So there's not as much force to balance out your weight because your speed is slower. For number 14, to weigh less in the Northern Hemisphere, you should go south. So if I want to weigh less, remember I want to go to where the tangential speed is really big. So tangential speed, Vt, is really big here. And right here, your tangential speed is a little bit smaller. And if you're standing where Santa Claus is, he is right there. That's why Santa Claus tends to be a little more round. And if you think of people that live on the equator in Brazil, they tend to be stick figures. They're really thin. So here is Santa Claus. Big hat here. His arms. Smiling. So anyway, nonetheless, let's go on to the next one, which is number 15. Possible space habitat of the future is a cylinder in space rotating about its long axis. What is the relative gravitational field along the axis of the habitat? So if you were right here, you would feel zero gravity. If you're out here, you're going to feel a lot of centripetal force, but when you get right in the smack dab center, you would float. If you whirl a tin can on the end of a string and the string suddenly breaks, the can will, remember, it will remove tangent to the circle. For number 17, a ladybug rests on the bottom of a tin can that is being whirled horizontally at the end of a string. Since the ladybug, like the can, moves in a circle, there must be a force on it, so we know that this is going to move in a circle in that direction, so it's going to come up this way. What exerts the force? Notice that there is a string here, but the ladybug is not connected to the string. The ladybug is connected to the can, so it's the normal force acting on it. The can is getting pulled by a tension force, so you have to look at each one of the forces individually on this one. People in the future, if you live inside of this thing, and it's more than 2 kilometers in diameter, people on the inside of the outer edge will experience 1G. But if you are halfway, so we said that right here at the middle, it was 0G. So if you're halfway to the axis, it would be 1/2 of gravity. And they say this would be really good for somebody that gets hurt. They could float into here. They'd still have a little bit, but not enough to really do too much to their body, and then as they got better, they could move back out to the full G of gravity that is right here. For number 19, it says stunt motorcyclist biker Bob rides his bike inside a futuristic space station. The normal force feels like weight to him as he's moving, as he rides the bike in the same direction as it is turning. So he's going in the same direction it is turning. His normal force will actually increase. So as he goes in the same direction, he's going to feel heavier. That's different than when he's going in the opposite direction. So if the space station is turning this way and he goes the opposite direction, after a while he will float because now he is experiencing no more speed. As this rotates, it's that speed. If we remember the equation, F is equal to mv squared over r, and if the space station is rotating in this direction and he's riding in this direction, they'll get to a point where his relative speed will be 0. And if this is 0, then we know his force is 0, or the normal force is 0. And he won't be able to do that. That is number 1 through 20. We'll do another video for 21 through 38.